welcome to the second lesson on this series of complex analysis. And in this video, we would be learning about complex analysis, how it emerged through the concepts and philosophical understanding. We will start primarily with Leibniz, and then we will see the emergence of the notation and how it can be visualized geometrically and many other interesting features which would make complex analysis not complex but much more easier. My name is Shaunak and you're watching this video on my channel Physics for Students. A warm welcome to the second lesson on complex analysis. Now, those who have watched my first lesson, I started initially with the interesting history of how complex analysis evolved, who discovered complex analysis, and various other features. So if you have not watched my first video, which is very interesting on the history part of complex analysis, I would recommend you to go into my playlist on complex analysis. The link is given there in the I button. So we start today even with much more interesting topics, and the topics of today's videos are construction of complex numbers, different properties which helps us in calculations, how the notation has been developed, and how can we visualize this geometrically, which makes mathematics much more easier. What is the modulus and argument of complex numbers, and the relation between argument and modulus through different examples. So this is the topic, and these are the areas that we would be learning. So it's a good time to start. So we start with a very famous, I would say, quotation which Leibniz did. And let us remember, during this time, with the time that we are talking about, complex number has not yet been discovered. There is a kind of, I would say, apprehension in what it is. And Leibniz says that the divine spirit found a sublime outlet in that wonder of analysis, that potent of the ideal world, that amphibian between being and not being, which we call the imaginary root of negative unity. What a wonderful and what a great quotation by the famous mathematician and polymath Gottfried Wilhelm Leibniz. Now, if you look into this kind of a quotation, you will see, okay, let me go once more, go back to the quotation. So there are two very important points. Now, why Leibniz call it as an amphibian? Because an amphibian lives both on the water as well as in the land. So the imaginary number during that time was imagine something which is between the real and the complex plane. So he calls it amphibian between being and not being, because during that time the numbers were the Pythagoreans developed number as something to be divine. So the divine spirit finally found an outlet which is almost like an amphibian living both in water as well as on the land, which is being and not being, and we call the imaginary root of negative unity. Now, this divine spirit found a sublime in that wonder world of analysis. So it was around 1702 that Leibniz made this quotation. And the current view of square root of -1, I would say a little bit prosaic through the unity made of its, at least is inspiring. So the logical status of complex number, which causes so much of distress, which used to cause so much of distress during the 18th century, is now seen to be on a very much in tandem with real numbers. So what puzzled the ancient scientists or mathematician was the obvious artificial and abstraction of the complex number system, in contrast to the apparently natural, concrete, real number system. So, but the mathematicians of today even sees the real numbers possessing a similar artificiality and abstraction. So we call it the obvious artificiality and abstraction of the complex number system. Now, we are talking of the time when Leibniz has discovered this, and still it was not, I would say, it was not fully in run, and there is a kind of an abstraction which I think still exists. So this is, I would say, the famous quotation and how mathematicians during that time perceived complex numbers. Okay, so now we will start with what we call construction of complex numbers. We will go slow, we will go step by step so that we understand the basic roots. Okay, so to begin with, we will take the examples of Bessel and Argand, maybe Gauss, or Hamilton. So it is said that a complex number is an ordered pair xy of real numbers. Addition and multiplication of complex number is defined by this and this. Okay, so if you're watching this video, what I would say is that you can pause the screen and take a quick note of this x1 y1 plus x2 y2, because we are using those two definitions of addition and multiplication further in this video. So it is very important for us to note that. So for example, I can take numerics like 3, 5, 2 and 7 and do it and get the value of something like minus 29 and 31. It's pretty simple. Now the question is that this definition, which is the culmination of several centuries of struggle and effort to complex numbers, it shows how elusive a simple idea can be. And you can say that we see these pairs have to do with square root of -1. However, we will now establish certain properties which will help to understand complex numbers much more in a better fashion. Okay, so the first theorem which I would like to tell here is something like this. The set of complex numbers with operations defined this and this one, okay, is basically called a field. That means z1 equals to x1 y1, z2 equals to x2 y2, and z3 equals to x3 y3. So these are complex numbers, and most importantly, they will satisfy the properties which we will just see now. So the set of complex numbers with the operations, as I told, the first and the second, is called a field, and it would satisfy a few of the properties. What are the properties? These properties are more or less similar, so I will just glance through it. It is addition and multiplications are commutative, that means this one. Addition and multiplication are also associative, which means this one. So you can just go through this simple. The addition, there is an additive addition of 0, 0, which means this one. And there is a multiplicative identity of 1 and 0 numericals, which is this one. And each element has an additive inverse, that means minus plus minus would result in this. And each element other than 0, 0 also has a multiplicative inverse, which is something like this. So I think there is nothing much to explain. These are properties. These needs to be understood and to some extent really memorized, so that the other theorems becomes much easier. Okay, so now the thing is that the multiplicative distributes are over addition, which we see this one. Now all this, the assertions of 1, 2, 3, 4, addition, multiplication, etc., etc., all of these are coming from this one, right? So for example, I would say this one, this multiplicative and distributive, this one actually comes because this from this, you can just check on the calculations, right? So what I'm trying to tell is that all these rules that we have just noted, 1, 2, 3, 4 others, they come from this rule that is which we just defined of the addition and multiplication. And I've just take an example that multiplication distributes over addition. The distributive property actually comes from this. Now we need to have one thing in mind, is that the symbol C, now it is not always this C, it might be a capital C with a little bit bold emphasis on that. It is basically a field of complex numbers. That is only what we need to understand, and this will be repetitive in nature. Okay, so now we try to discover what Leibniz and other mathematicians discovered, the notation x plus iy. Now the symbol is commonly used as a complex number is not xy, but this one, x plus iy. This actually goes back to Euler during the time of 1779, who used to denote square root of -1, though the notation actually goes back again to the Prince of Mathematics, Carl Gauss. But if you really want to know more about the history of how this notation etc. have been discovered, go back to my very first lesson on complex analysis, where you will find a detailed history on this. Okay, so now to recover this notation, let us discover how this notation can be interpreted in terms of mathematics. Okay, so we know this one, right? x1 0 plus x2 0 would be equal to this, and we also know this. So what happens from these two definitions, we may identify a complex number which is this one, and this would be with the real number x1. Okay, so we identify a complex number x1 comma 0 with the real number x1. So in other words, what we can say that if I take x1 0 as a kind of a map, right, which maps up to x1, it defines a kind of an, I would say, an isomorphism or similarity. Let us call it similarity, right? And kind of a similarity or isomorphism between the set of complex numbers in the form of x1 0 and r, which is a real number. Right. So we define x1 0 in terms of x1, which is a real number, which maps to x1, and it defines a kind of a similarity or isomorphism between x1 0 and real r. Now let us define, for example, I equals to 0 1. Then from there we get x plus I1. We just do the algebra and we get this. And then further we get this one. And this actually comes from this, right? So I've just given this one and this one. So sorry, x comma y actually comes from so these two. That is why I told you to make a note. Now further solving, we get I square equals to this, and then we get this, and finally we get minus 1. I mean to say, this is just an analogy which I'm trying to show and discover the notation from. Then we might say that I equals to square root of 1. Sorry, square root of minus 1. So the x plus iy, this notation is more convenient, and we will use it from now instead of using something called x plus yi, right? So this comes, these two, z1 plus z2, this actually represents the same number in particular. We use the form xy are specific real numbers because 1 plus 2i looks more sensible. That is why there is a tick 1 rather than, so these two numbers, as you see that it comes from here. And we generally take the notation of 1 plus 2i because it looks more sensible than so it's green tick rather than 1 plus i2. I mean to say both of them are correct, but it's the sense that which one looks favorable in terms of mathematical calculations. Now having said this, and we have defined and more or less intuitively or mathematically we have arrived at how I equals to square root of minus 1, what Leibniz told as amphibians, which is within the being and not being. And we will now see quickly what are the advantage of getting this kind of a notation. So one is that this is more convenient. I'm to say more convenient in terms of doing mathematical calculations, etc. Second is that the algebraic computations becomes much more easier with this type of a notation. And third is that all the algebraic rules, I mean to say, in general, all the algebraic rules are basically are followed. So these are the major three, I would say, advantages of using x plus ay or a plus ib, whatever be the notation that we do. So now the thing is that because they use all the algebraic rules plus the rule I square equals to minus 1. So in order to multiply, we work out this one, right? This works out if you use using I square equals to minus 1, and this one also works out, right? But I square equals to minus 1 when because I square equals to minus 1, so the next equation turns to this, right? So this is how it happens. So just to let you know the algebraic notation, how it is favorable and how the equation changes. And remember that this one is basically what we call the choice of multiplication formula, which we have seen earlier. Now we come to something which is called the geometric interpretation. That means we will see geometrically all those things that we have learned, and it helps us to visualize in a much more better way. Okay, so this is the figure. I mean to say a graph which I have given the real and the imaginary part. So when a complex number a plus ib is actually kind of plotted on an argand plane, so we call the x-axis as a real axis formed by real numbers, and y-axis is considered to be y as the imaginary numbers, and this is how it forms a plus ib. We will expand on this, don't worry. So if we get a kind of a real plane, I mean to say a plane where these numbers starting from 0 goes to positive and negative. So this is the real number, this is the real number. The question is that if I get a kind of an equation like 3 plus 4i, then where do we really put it across? So what we do is that imaginary number goes up and down. So if this is the kind of a graph, so I will work 3 steps towards the right, somewhere here, and then I will go 4 steps towards up, and this is a kind of a position where we plot 3 plus 4i. So I go 3 units up along the real axis and 4 units down the imaginary axis, and somehow I get to a point where I plot 3 plus 4i. So that is why I told this is a visual interpretation. So similarly, if I get 4 minus 2i, I will go towards 4 in this way, and I will go downwards because the minus 2 is in the imaginary quadrant section, and I go somewhere as this. So 4 units along the real axis, 2 units down the imaginary axis. So complex plane is because of its combination of real and imaginary and plane. Why? Because obviously it's a geometrical plane. So this is a nice way in which we can visualize things. Okay, now we come to something very important, which is called the modulus of a complex number. Okay, so what it is? Very simple. So what we do is that we get a kind of a distance from the origin 0, 0, which is called the modulus of that complex plane. So here it is. These are the 2 figures which I have obviously taken from the internet. So you see from 0, 0, there is a line which is drawing, and this is called the modulus of that complex number. So considering the complex number z equals to x plus iy, which is plotted on a complex plane, it actually creates a kind of a triangle like this one, OXY. Okay, so with its x-axis as the base as x and the perpendicular as y. So the distance of the point from the origin is the length of the hypotenuse, r. So we use the simple Pythagoras theorem and we get this one. So the modulus of a complex number is represented as this double bar z, and we can also tell that the modulus of a complex number is this one. And further we can also tell that this is z equals to real part squared plus imaginary part squared. This is just a kind of a quick example. Okay, there is something which is called an argument of complex numbers. So what it happens is that the length of the line segment, that is OP, you can see here, is called the modulus, and the angle which forms is called the argument. Mind, the spelling is not the normal argument which we mean in English. It is ARGU. So that is how it happens. So this is the angle of argument Z, and this is the axis, this one. These are all, demonstrations of how the argument changes and the axis changes. And for a complex number z equal to x plus iy, we get theta equals to tan inverse of y upon x. So that is how the argument, we will see more examples, things will become clear. Okay, so let us see an example, and we want to find the modulus and argument of z equals to 4 plus 3i. So the complex number z equal to 4 plus 3i, what we first need to do is that we need to draw this, right? This has been represented on point Q, which has coordinates 4 and 3, and the modulus of z is the length of OQ, which was this one, and we again use the Pythagoras theorem, and we get 5. So hence the modulus is 5. Very simple, elementary. So the modulus of z equals to 4 plus 3i is 5. This is the triangle that follows. This is the angle. Now mind it that to find the argument, that is the angle, we must calculate the angle between the x-axis and the line segment OQ, which is this angle given in red. So by referring, because it is a right angle triangle OQN, what we do is that we get tan theta equals to 3 upon 4, and theta becomes tan inverse of 3 upon 4, and you can calculate the degree as 36.97. So what do we summarize from here? We summarize that the module of z equals to 4 plus 3i, which is this one, which is and this is the theta angle, which is 36.97. And what we get is that we write it in this way. There's a special symbol to the modulus, that is its double bar. So this example double bar is z equals to 5, and we write it as ARG, that is we call the argument abbreviation, and it measures 36.97. Okay, now we see a little bit of relation between argument and modulus, and this is very important. So I would request not to skip this part. Okay, so here you see that the polar form of a complex number is written using this one. So if we draw this one, so what we get is that we get sine theta equals to x equals to r sine theta, Then we get cos theta equals to y upon r equals to r cos theta. Then we get x plus iy equals to r cos theta plus I sin theta, and the polar form of the complex number is written as this. Now this is basically the polar form in which we are writing the complex number using the modulus and argument of that complex number. Now if I use the geometric representation, I think this will become clear. Okay, this is something you're quite familiar about, and I have no point in explaining these things to you. So now remember, when we are calculating the argument of a complex number, there is a choice to be made where the values are between minus pi and plus pi. You can see that. So, and the range is because between 0 to pi, you can see the x-axis. Now both are, I would say, equivalent and equally valid. Now the basic way of calculating this is to calculate a comma b, which is the arctan. But since arctan has a range value of minus pi by 2 to plus pi by 2, this will bring a wrong impression. So we have to, with negative components, so we need to subtract that. So let us see. So this is the first quadrant that we are dealing about. You can see the xy axis moving in this, and we call the first quadrant as theta equals to arctan p by a. Then we go to this side, that is the second quadrant, and you see that the axis has, the angle has changed, and this is plus pi. So the value would be theta equals to arctan b by a plus pi. Then we move to the third one, this one, and you see the axis, the angle has changed, the line has moved this part. So here you will see that there is a minus pi. So it would be arctan b by a minus pi, and the fourth quadrant would be simple arctan b by a. Now this is a kind of a visualization which helps you to understand that if things are the relation between the argument and modulus, in which quadrant and where it is going. Now here is something very important. Now you just note that in the case when a equals to 0, I mean to say it means that the complex part has really no real part. In that case, the arctan method won't be working out. This is very important. But the argument is either pi by 2 or minus pi by 2. Yeah, you see this one. Argument should be pi by 2 or minus pi by 2, right? So for numbers with positive and negative imaginary aspects respectively. So we do what we do is that, okay, yeah. So this is important. So for numbers with positive and negative imaginary parts. So in case that when a equals to 0, the arctan method doesn't really work out. Okay, I will just show you a quick example which will make further things clear. So if I take z1 equals to 1 plus I, then what we get from here is that we get the argument and we further calculate, we get arctan equals to pi upon 4. Now the same calculation, for example, if I take z2 equals to minus 1 minus I, it gives an arctan of minus 1 by minus 1, which gives pi by 4. Now note that this one and this one both are the same value. So if we draw now a z2, it will come somewhere in the on the Argand diagram. If you draw it, then it will fall somewhere in this third quadrant, somewhere here. So the argument should be minus pi and minus pi by 2. This one, the marked in red. So we must subtract one from the other. We must subtract the pi, and what we get is z2 equals to minus 3 pi by 4. Okay, so this is basically the relation between argument and modulus. I won't be extending this video further because I need to show in the next video the geometric representation of addition, multiplication, subtraction with the complex numbers in the complex planes. So let us summarize till now what we have learned. So we have learned how the complex numbers emerged. We also learned the theorem and the properties. We found out a kind of a derivation, semi-derivation on x plus iy. We find the advantage and disadvantages of this notation. We visualize the complex numbers using how we move, the argument, modulus, the connections in different quadrants, and so on. So in the next video, what I would do is that I will expand a little bit on the geometric visualization of the different operations of complex number, and then we will go further. So that's it for today's video. Please put up your comments and let me know how things are. And this is Shaunak signing off from today's video. Please subscribe to my channel Physics for Students and click on the bell icon to get all the notification from Physics for Students. We'll be back and continuing this series on complex numbers. Further on, a lot of videos to come in the near future. Thank you very much and wishing you a great day ahead. Goodbye.
Thank you for watching this video. We appreciate your time and patience. If you want to connect with us and provide further feedback, comment or suggestions, please email us at contact.physicsforstudents@gmail.com. You can also follow us on Facebook, Instagram and LinkedIn. See you soon in the next video.